Welcome to Ask and Learn.
In this problem, we are told that we can find this thing called the logarithmic decrement, and that is allow us to find a damping coefficient from the from experimental data that we collect. And how we can do that is it's essentially fitting an exponentially decaying oscillation to whatever data we've collected, right? So we can look at peaks. We can look at either subsequent peaks. That's usually what we do, is look at subsequent peaks. Although you can look at multiple peaks and generalize this a bit, but things will change a little bit down here. But if we look at one peak and then the next peak, we know that at a peak, this thing is a maximum, so this is 1. So our peaks are just given by this expression, and so we have exponentially decaying. Each peak decays as an exponential. So the first peak at T1 and the second peak occurs at T2. And so the ratio, again using the ratio, D cancels out, and then we can use our properties of exponential functions to write it this way. Then we also know that these peaks, the time between two successive peaks, is the damped period, or the damped natural period, which is 2 pi over the damped natural frequency, and the damped natural frequency is omega n times the square root of 1 minus the damping ratio squared. So we know what this is from here, and so we can take that, so we take this, plug it into here, and so we get this ratio of the amplitude at one peak to the amplitude at the next peak is e to the 2 pi zeta all over square root of 1 minus zeta squared. And that happens because the natural frequency cancels out here when we substitute this into here. We can take the natural log of both sides of this, so we get the natural log of this ratio, and that is a function of zeta alone. And so if we measure these two things, we can calculate this value and then solve for zeta. And if zeta is small, then you can, a lot of times you can, well, if you know it's small because it's not, the amplitudes aren't dying out really fast, you can a lot of times get away with approximating this just by 1. And so that zeta equals the logarithmic decrement divided by 2 pi. You can generalize this a little bit if you don't want to take subsequent peaks, but adjacent peaks, but if you want to take, say, here and here, and that just means that you have more periods here. So you would have, say a number n, where you have the first peak and then the n plus 1 peak. So you'd have n in here, and so that would propagate through here, and you'd have to just know how many peaks apart each of these are. And that can give you a better approximation, because subsequent peaks, can be a little misleading, especially if there's a kind of other kinds of energy dissipation, like Coulomb friction and stuff in this system. But this is a good way of getting an estimate of the damping coefficient, or the damping ratio.